All right, so in this video, we're going to talk about infinite series. Now, when you talk about series versus sequence, on the surface, there doesn't appear to be much of a difference, right? A series is just the terms from a sequence that are added up. But when it comes to talking about convergence and divergence, things do get to be very, very different in how we need to approach them. So what I have up here on the screen so far is just a standard infinite series. You can see the notation is sigma here. We're going up to positive infinity, and I've laid it out term by term. A sub 1 plus a sub 2 plus a sub 3 plus a sub n plus, and then we continue on. So there's our standard infinite series. Now we're going to go a little deeper into it. This is going to be an infinite series where s sub 1 is going to equal a sub 1. S sub 2 is going to equal a sub 1 plus a sub 2. You can probably see the pattern here. We'll go all the way down to s sub n equaling a sub 1 plus a sub 2 all the way plus the a sub n term. Now, these are called partial sums, and that makes sense because it's not the whole sum, it's just parts of it. So these are partial sums. In particular, this guy right here is called the nth partial sum. And we'll take that nth partial sum now, and we're going to rewrite it in its sigma form. So that's going to be now a sum from I equals 1 to n of a sub I. Okay? Now, we've got our nth partial sum. And as I mentioned before, if we take away the sum part, we can then view it as a sequence. So now we're going to define s sub n from n equals 1 to positive infinity as being the sequence of partial sums. Sequence of partial sums. And that's going to be important. It's going to be important because here in just a second, we're going to talk about this idea that if the sequence converges, maybe I'll write that down. If the sequence converges, then the series also converges. And we've spent quite a bit of time in the last section talking about sequences and getting them to converge or if they happen to diverge. So again, that sequence of partial sums is going to be really important for us. So I'm going to go ahead and move this up a little bit, and I'm going to lay out then a definition. And that definition is essentially just a summary of this idea. If the sequence converges, then the series converges. So I'm going to start with the limit as n goes to positive infinity of s sub n. Okay, so that's going to be the limit of the sequence of partial sums. And now we're going to walk it back a little bit. We're going to walk it back into some notation you would have seen in Calc 1. We know that that's going to be the limit as n approaches positive infinity. And for right now, I'm just substituting this guy in right here for s sub n. We know that they're equal. This guy and this guy are the same, so I'm going to take this and I'm going to plug it in right there. So that's going to be the sum now from I equals 1 to n, a sub I. And walking it back another step now, we're actually going to do away with the limit notation that I accidentally wrote. We're going to now view this as an infinite series from I equals 1 to infinity of a sub I. And so I mentioned some Calc 1 notation. We saw this when we dealt with infinite sums when it came to the Riemann sum and how we had to then talk about this limit going to infinity. So now we're just kind of moving a little bit backwards. And so this guy then ends up being our actual sum. So if we go ahead now and we are convinced that if the sequence of partial sums can be found, that our series then would converge to that same S. All right, so we're going to take a look at an example now, and hopefully it'll break apart what I just talked about in that previous screen a little bit more and be a little bit more clear in terms of what we're trying to establish. Now, we're going to go ahead and see if we can figure out what this thing converges to. And so we're going to do so by using the partial sums. We know that S sub n is really just going to be the nth partial sum from I equals 1 to n. So now we're going to have this 1 over 2i minus 1 over 2i plus 1. And so double check the notation from the previous screen if you need to. We're now going from I equals 1 to n, so these would need to be our I values there. Okay? Now I'm actually going to take a little bit of time and write out a few of these terms. So if we start with I equals 1, that's going to give us a 1/2 minus 1/4. So we get a 1/2 minus a 1/4. Okay, so that was our first iteration. Then plus, if I equals 2, that's going to give us a 1/4 minus 1/8. So 1/4 minus 1/8. And then the next one, if I equals 3, that's going to give us a 1/8 minus 1/16. So 1/8 minus 1/16. And then this would continue all the way till the very end where we evaluated at n. So we're going to have this 1 over 2 to the n minus 1 over 2 to the n plus 1. All right, so now this is called a telescoping series, and it's because it's kind of collapsing in on itself like a telescope might. You can see then that the 1/4 being negative and the 1/4 being positive go away. Same thing there. And if we were to continue, you would also notice the same pattern. Now we're going to have to be a little bit forward thinking in what's about to happen here. Notice how it's a negative to start followed by the positive. Negative to start followed by the positive. So over in here, one of the ones I didn't write was the negative one of these. So I've got a negative 1 over 2 to the n sitting right here, and it would then in turn do away with this guy right there. So when all is said and done, S sub n is going to be 1/2 minus 1 over 2 to the n plus 1. So now, since I've got a sequence, I'm going to take limit as n goes to positive infinity of this 1/2 minus 1 over 2 to the n plus 1. And when computing this limit, this guy will go off to 0, leaving us with a sum of 1/2. So in order to find what this series converges to, we looked into the sequence of partial sums and were able then to compute the limit as we did in the last section, coming up with our 1/2.